In a previous video, we looked at integrating by reversing the chain rule, and we did that when we had a product. This video is about integrating when you use a substitution. The chain rule exercise worked where you had a product where one of the factors was the derivative of the other. However, not all situations are going to be like that, as this example below shows. I don't have two things being multiplied together here. How am I going to go about factorizing it? How am I going to go about integrating it? Well, the trick is to use a substitution. Let's get some lines on this page. Right, and the substitution is going to look like this. I'm going to say, let b equal that thing that I've got inside the bracket over there, 2x minus 4. Now, I've got a function there, b in terms of x, so I can say, right, db dx is going to be simply 2. Now, if I do that, I can just take this one step further, and I can say that db is going to be 2 dx. Now at this stage the integral looks like this. It's the integral of b to the power 3, but then I've got a dx over here, and I can't integrate something that's b to dx. I've got a db over here, which would be useful, but I've got to have a 2 dx's over there. So how can I deal with that? Well, what I'm going to say is, I'm going to say, right, this is going to be a half times 2. That's going to give me 1. And if I multiply by 1, I don't change the value of this thing. Dx. Now I can take that half as a factor out the front. I've got the integral of b cubed, and then I've got 2 dx. And 2 dx, as we've seen from over here, is the same as db. So I've got the integral of a half of b cubed db. Now I'm in business. Now I've got a simple, straightforward integral. B is going to increase by 1 power, but I must divide it by 4. And then I've got to add on c, and I've got to multiply this whole thing by a half. Need a bit more space. Having done that, all I have to do now is to go and substitute back in the thing that I started out with. And so this is going to be a half by a quarter is going to give me 1/8. 1/8 b, and b is 2x minus 4 raised to the power 4 plus c. And there I have my integral. And I've used a substitution in order to make the thing easier for me. Now there are various other adaptations of this that we need to look at as well. So let's take a look at this example here. The integral of x times 3x plus 2 to the power 5 dx. Aha, it's a product. Is it the inverse chain rule? No, it's not. Because the derivative of 3x plus 2 is not x. So I can't use that reverse chain rule. So what I need to do is I need to make a substitution. So I'm going to say t is equal to this 3x plus 2. Oopsie, sorry. And that means I can say that dt dx is going to equal 3. I can also, with this statement over here, rearrange this part. And I can say that x is going to be t minus 2 all over 3. Now that might be useful at a later stage. Let's see. Let's go back to the integral and see what it looks like when I put my substitution in. So I've got an integral now. I've got x. My bracket is easily put in. It's t to the power 5. And then I've got dx. If I rearrange this, I can say dt is going to equal 3 dx. But I could always rearrange that and say that dx is going to be equal to dt over 3. If I've got that, that means that I can put it in over here. So that's quite useful. But I still haven't dealt with this x at the front over here. Well, in some ways I have, because if you think back to this rearrangement that I did over there, I can rearrange that substitution and express x in terms of t. So I can rewrite this integral. Instead of x, I'm going to write t minus 2 all over 3. And then I've got t to the power 5. And then instead of dx, I'm going to write dt over 3. Now I've got a lot of fractions in there. I've got this first factor that's got a fraction with a denominator of 3. I've got this dt over 3 at the end over here. So I'm going to take out 1/9, a third times a third. And that's going to leave me with the integral of t minus 2 times t to the power 5 dt. And all I need to do now is to expand that bracket. So I've got 1/9, the integral of t to the power 6 minus 2 t to the power 5 dt. And now it's a simple integration, the likes of which you would have done last year. So this is going to be 1/9 t to the power 6. The 6 becomes a 7, and I divide by 7. Put a big bracket around that. And then I've got 2, it is t to the power 5, so this has got to become t to the power 6, and I'm going to put that all over 6. And then I'm going to add c to the end of that. And so, when I tidy this up now, I'm going to get t to the power 7 over 63 minus, what have we got here? 1/3 times 9. I've got t to the 6 over 27 plus c. I know it's c over 9, but it's just a number at the end. We can deal with that later. But if you remember, the expression didn't have anything to do with t's, it had to do with x's, and we said that t was 3x plus 2. So all I have to do now, oopsie, too far. All I have to do now is to go and put in over here 3x, was it 3x plus 2? Yep, 3x plus 2. 3x plus 2 to the power 7 over 63 minus 3x plus 2. I don't know why I put a 2 over there, it should be a 6. (3x plus 2 to the power over 27 plus c). Obviously we can tidy that up a bit further, but I think that is good enough point to which to leave that. Now there's one more thing that we need to be careful of when we're dealing with these type of substitutions, and that is when you're working with a definite integral. If you're going to make a substitution, you must make sure that your extremes, these values over here, are taken into account when you make a substitution. So let's take a look at this one. Well, I'm going to start off and just, before I do anything much, I'm going to rewrite this as x minus 1 to the power of a half dx. I think it's just going to be easier working with an index rather than with a square root sign. And I'm going to substitute. I'm going to say let x minus 1 equal a. That's all good and well. That means that dA dx is simply going to equal 1. In other words, dA is going to equal dx. That's simple enough. However, we also need to consider what is happening with this thing, x minus 1. So at the point when x is equal to 1, x minus 1 is going to equal 0. So that means our lower bound is going to change to not 1 but to 0. At x is equal to 5, the upper bound is going to be 5 minus 1, which is going to equal 4. Sorry, I shouldn't put x over there. I should put 1 minus 1. And so my upper bound is now going to go to 4. So these are my two new bounds. I can now go back to my initial integral and rewrite it in terms of the substitution that I'm going to use. So it's going to be the integral, not between 1 and 5, but between 0 and 4. Not of x minus 1, but of a to the power of a half. And we can see that dA and dx are the same, so I can write this as dA. Now I've got a simple integral that I can work with. My power of a is going to increase by 1, so this is going to be a to the 3 over 2. I'm going to divide by 3 over 2. And it's a definite integral, so it's going to be between 0 and 4. I can rewrite this as being a to the 3 over 2. And instead of dividing by 3 over 2, I can multiply by its reciprocal, which is 2 over 3. And I want to work out that between 0 and 4. And now, if I go and work that through, what have I got? I've got 2/3 4 to the power of 3 over 2 minus 2/3 0 to the power 3 over 2. And so this is going to be 2/3. 4 is just 2 squared, so 2 squared raised to the 3 over 2 is going to be 2 to the power 3. And so I'm going to get an answer of 16 over 3. And there is my integral. That's just about all for now. I will make another video for substitution where they use trig ratios. I put it in as an extension because it's not really in the syllabus. They haven't really asked it, but I put it in just as an addendum for you to work with. So have a look out for that if you're interested. If not, just work on this and make sure that you get it right. Thanks. Goodbye.